Hello and welcome to lesson 2.3, definite integrals and antiderivatives. So we're going to see that there is actually a link between definite integrals and antiderivatives, which you might have already noticed by this point in time, but haven't really talked about specifically. So first of all, we're going to talk about some rules for our definite integrals, and then use those rules to figure that out, and then we're going to see the link between the definite integral and the antiderivatives. So first off, notice that if your bounds go from A to A, you're not actually finding any area. And that's why that is just the value of 0. Now, if you have an integral going from A to B, it's considered to be negative if it goes in the opposite direction. You can always take a constant out of an expression or an integral. If your bounds go from A to B and then from B to C for the same function, then you can link them together and just make one integral from A to C. Also, if you have two functions that are bound on the same values, you can actually separate them, find the area of one, find the area of the other, and then add or subtract that result. The last part tells you in order to find the area of something, it can be bound by the minimum of the value of a function and the maximum value of a function. So that one's going to take a little bit more to describe here. So let's suppose I draw a function f of x. And you want to find the area from A to B. So that's this area right here. Well, if you look at the maximum and the minimum, the maximum right up here and the minimum, I'm going to try a different color right down here. So the minimum is this area given by the blue square, and the maximum would be this square. And then you can see the red, the add area, does fit in between the verb and the blue. So it makes perfect sense there. Okay, so that's based on that aspect. So now let's talk about using these to evaluate. So let's suppose we have an integral from -2 to 1 for f of x is equal to 4. We have an integral from 1 to 3 of the same function is equal to -5. And we have an integral from 2 to 3 for f of x, which is equal to -2. So let's suppose we have that there. Okay, so if you want to calculate the integral from 3 to 1 of f of x dx, I'll realize that 3 to 1 is different from 1 to 3. So that's equal to the negative of 1 to 3 of f of x dx. And that's one of our properties. So if that value is -5, so negative of -5, that means this answer turns out to be 5. Okay, so now look at this one. This goes from -2 to +3. So what we can do is we can separate this into two integrals from -2 to 1 of f of x dx plus 1 to 3 of f of x dx. Because the two of them combined make up one full area. So I know based on the first piece, this is equal to 4. Our second piece is equal to -5. So the two of them together are equal to -1. Okay, this next one can be a little challenging based on what you can see. So we want the integral from 1 to 2. Well, you notice none of our expressions have the value of 1 to 2. But one does have 1 to 3, and the other one has 2 to 3. So what if I take this result and I add it to the integral from 2 to 3 of f of x dx? Because I do have that amount. And I know this is the integral from 1 to 3 of f of x dx. I know that those two are equal to each other. So, what I can do is I can now still call this 1 to 2 f of x dx. Going from 2 to 3, I know that's a value of negative 2. And I know this is a total of negative 5. So now, it's just a matter of rearranging this equation. So negative 5 minus negative 2. And we get this value as negative 3. Last but not least, we're going to try to solve this last one. Well, notice the balance going from negative 4 to 2. Well, again, we don't have any negative 4. Because we don't have any negative 4, this one is impossible to solve. So that's all we are going to be able to say. We're not going to be able to solve this no matter what we do. Okay, let's move on. Okay, so we get some definitions and some ideas here. So if f is integrable, in other words, you can calculate the integral on this domain a to b, its average value is defined by this expression. The average value of f is equal to 1 over b minus a of the integral from a to b of f of x dx. And based on the mean value theorem for definite integrals states, if f is continuous on a to b, then there's some value c that exists on the domain a to b where f at c is equal to this b minus a times the integral from a to b for f of x dx. And if you take a look at this now tells you f at c times this length of b minus a is equal to that integral from a to b of f of x dx, which you can see is given by that green box right here. That's that value of b minus a times f at c. So there is some value c somewhere on that domain that will make that area equal to the area underneath the curve of f of x. So we see this commonly used on the AP exam. We see it being used to calculate average velocity and average position many times. So you'll be asked to calculate an average velocity or an average position based on a velocity or position function that you're given. So you're going to have to use this formula from time to time. Okay, so now we're going to get into what they call the Fundamental Theorem of Calculus. Okay, so what we're going to do is we're going to first recall the definition for the derivative of a function. And we're going to state capital F of x is equal to the integral from a to b of f of t dt, which is given on the very far right of this drawing. So we're going to say this area underneath this curve is called f of x up to some value x, where x is somewhere in between a and b. Okay? So first of all, we're going to go back to our derivative function. So we're going to call capital F prime of x equal to the limit as h approaches 0 capital F of x plus h minus capital F of x all over h. This was a derivative definition that we saw in advanced functions. Okay, so now what I'm going to do is I'm going to substitute. Now capital F of x plus h is just given by the integral from a to x plus h of f of t dt. And this one's just a to x of f of t dt. Remember, this is all over h. Okay, well, based on this idea, noticing that these two lower bounds are exactly the same. One is going up to x, and one is going up to x plus h. For taking that, and this is, so just drawing a little extra onto this graph to the right, let's say x plus h is this area right here. So we're going from a to x, and then a to x plus h, so I'll draw that in red. We're subtracting those two areas. Then notice this area that's being left over when we subtract it just gives us our limit as h approaches 0 of the integral from x to x plus h of f of t dt. This is still going to be divided all by h. Okay, so based on what we just talked about up here, there is some value c where this, on this domain, they'll make this expression true or this expression true. So, that being said, based on the mean value theorem for definite intervals, there exists value c on the domain from x to x plus h, such that f of c times h is equal to the integral from x to ax plus h of f of t dt. And so, that now makes our first derivative equal to this expression right here. You can cancel out the 1 over h with the h, because it's a limit. You can cancel it, so that's all right. And then you're left with the function f of c. But c is on the domain from x to x plus h, where h is approaching 0. So that's just equal to f of x. So that means the derivative is equal to f of x. And that means now this piece right here stays, and this piece is just the derivative of that f of t, which we talked about as antiderivatives. So we call this one the antiderivative. Now if we substituted a into our expression, a right here and a right here, we get f of a plus c. Now you know this domain, or sorry, this area is equal to 0. So f of a plus c is equal to 0, and that means negative f of a is equal to value c. So now this gives us this expression, which is called the Fundamental Theorem of Calculus, technically called Part 2. Part 1 was actually the derivative aspect of it. So this part right here, that's part 1. Okay, so now what we can do is we can use this idea to actually calculate values. We can actually calculate the area underneath the curve because if we know the antiderivative, we can figure this out. So we're going to do this with our example here, our second example. Okay, so first of all, right here, this is the function f of t equals t. So we have to think back, what is the antiderivative of such a thing? Well, the antiderivative of this is a half t squared. You don't have to worry about the plus c aspect of it, because the plus c is going to be dealt with by that negative f of a part. Okay, so this is how we write this. So to calculate the integral from 1 to 3 of t dt, noting in our mind the antiderivative is a half, what we commonly do is we write square brackets. We write down a half t squared in the square brackets, and we write the 3 up here as a superscript and 1 as a subscript. What we now do with that value, take the half, we place the 3 in for t first. You always do the superscript first. Then you subtract a half. You substitute 1 in now for the value of t. Once you get these values, you just calculate them. So this turns out to be 9 over 2. This one turns out to be 1 over 2. This turns out to be 8 over 2, which is the value 4. And now we found out the area underneath the function, which I'll prove to you right here. So we have the function y equals t, going from 1 to 3. Find out this area. Well, you can break this up into multiple areas, or you can do a number of different options, but I'm just going to separate this using a rectangle and a triangle. So first of all, the rectangle is a 2, and this one's height of 1 unit right there. So this is going to be an area of 2. This height from here to here, since this value is equal to t, this is 3, so this is 2 units height. This is 2 units length, but that area right there, that area is 2 times 2 divided by 2, because it's a triangle. So that's going to be 2. So one area is 2 units, one area is 2 units, 2 plus 2 is 4. So that proves that these two work and give you the exact same value. And thus concludes this lesson.